Hi everyone, thank you so much for tuning in to my mini lecture. I'm doing a quick lecture on glycolysis. Hey, what's the main point of glycolysis? I thought about my absolute favorite food, which is ramen, and I actually wanted to understand how exactly do I get energy from ramen? Well, glycolysis is exactly how we harvest chemical energy to eat and to be able to move and be able to do the things that we want to make energy. So, this glycolysis is how chemical energy is harvested from my case, ramen. Maybe yours is another food. And typically, food energy is stored as ATP. And right, typically you don't use the energy that you eat right away. Sometimes you have to store it for later use. And that's why ATP is such a powerful molecule. So, glycolysis is a catabolic, exergonic, and it's an anaerobic process. And remember that glycolysis is for MCAT purposes, we have to remember that big picture. We have glucose. Here's our glucose. It gets oxidized to CO2, and we have oxygen that gets reduced to water. That's the big picture that we look at when we talk about glycolysis in terms of what actually happens. And that's what we mean by glycolysis is an oxidation reduction reaction. So, how are we going to learn about this? Basically, we'll talk about quickly the location of where this actually all occurs for all these processes. So, location, location, location. Where does this happen? When it comes to glycolysis, glycolysis occurs in the cytosol of the cell. And you might ask yourself, well, does it need oxygen? No. The answer is no. Glycolysis is an anaerobic process and therefore does not need oxygen. How about the PDC and the Krebs cycle? Where does that happen? Well, for the PDC and the Krebs cycle, this occurs in the mitochondria, the matrix of the mitochondria for the PDC and the Krebs cycle. And you might ask yourself, well, does that need oxygen? And the answer is, well, yes. However, it needs it indirectly. So what does that mean exactly? Basically, the PDC and the Krebs cycle, they do not use oxygen directly. However, if oxygen is not present, then it cannot run. So I have a short little expression for that, which is we don't use O2, but if there's none, it can't run. And that's for PDC and the Krebs cycle. And the last one that we'll talk about is the ETC and the oxidative phosphorylation. So this happens in the inner membrane of the mitochondria. And does it need it? Does it need oxygen? Yes. Oops. Yes. It does need it and it uses it directly. So those are my little hints. This, is for the matrix of the membrane. And I put a little question mark because it uses it indirectly. And this one is a direct yes. So I'm going to have 4 quick slides that talk about what we need to do great on the MCAT to understand the glycolysis. At least the parts that we need to understand well so that we can perform well. That is what happens to the carbon chain, where are those regulatory points, names, and energy in and energy out. So, first part, we have the structure, and we're just going to talk about structure of the carbon chains, right? Carbon chains. So, we start out with 6-carbon glucose. We first phosphorylate it. Then we isomerize it, which means we change it. Then we go ahead and phosphorylate it again. First we had 1, now we have 2. Then through a series of steps, we dephosphorylate it. That phosphorus is gone. Split it in half, and then we're going to end up with 2 carbon molecules. So that's just the structure. So now let's talk the name game. What are the important names that we have to know for glycolysis? Well, this first molecule here is called glucose, and glucose is what we use for glycolysis. The next important name that we want to focus on is this molecule right here, which is a fructose, and it's a fructose 6-phosphate. So any of the P's that you see here, they're all phosphates. The next name that we want to talk about that's going to be really important is the pyruvate, which is at the end we have two 3-carbon molecules that we are able to obtain from this entire process. And pyruvate is an important name. So the 3 important names that we have to know is GFP, that's glucose, fructose 6-phosphate, and pyruvate. These 3 molecules are going to be important names when it comes to the MCAT and talking about glycolysis. So, what about the other names? I'll mention them quickly, and I'll start from the bottom and go up. When it comes to this PEP molecule right here, this is phosphoenol pyruvate, and this is going to be seen in gluconeogenesis. Next, we have GAP, that's glyceraldehyde 3-phosphate. And then this other molecule right here is a fructose 1,6-bisphosphate. So it's a double phosphorylated fructose. Okay, that's it for the name game in terms of the molecules' names that we have to know. So let's talk energy in and energy out. So before you get worried, let's just focus on this area right here. And these are kind of just my little side notes. So same picture. What we're looking for now is where does the energy go in and where does the energy go out? Where? Well, when we come to this first molecule here, we first invest 1 ATP. Now, I know that you know that when we have 1 ATP that goes in, that means we have an ADP going out. But for sake of clarity, we'll keep this clear. And next, we have this ATP here at this molecule, the fructose 6-phosphate. Another ATP is going to be invested. And again, since this 1 ATP went in, then 1 ADP will come out. ATP in, ADP out. ATP in, ADP out. So far we've invested 2 ATPs. Now, through a series of steps, by the time we get here to this molecule, this 2,3-carbon phosphate, we actually finally produce 4 molecules of ATP. Also, we produce 2 molecules of NADH. So again, hey, remember, if we produce this 4 ATP and this 2 NADH, that means that the ADP went in 4 of them, and then 4 ATP came out. When it comes to the NADH, we had 2 NH, and we had NADH come out, 2 of them. So NAD, NH, and NADH come out. So, what does that mean? Let's do a little math, shall we? So basically, our math over here is that we have 4 ATP made minus 2 ATP, and 2 and 4 minus 2 is 2NET or 2 net ATP molecules from this reaction. Next, my absolute favorite part, and the last part. Now, let's talk about regulators. I want to zoom in really quick on one of my absolute favorite songs, which is Warren G Regulate, featuring Nate Dogg. And those regulators are awesome, and they're tough because regulators tend to have to be big and spontaneous, and you can't reverse them, right? They run stuff. So we have to be on the safe side with regulators. And I use this analogy to express the regulators that occur in glycolysis. So let's take a look at these two regulators, and we'll take a look at this final important one. So let's talk about the regulators. This first regulator in the process of glycolysis, it happens after this glucose molecule, and its name is hexokinase. Now, something important to express is that if you have a kinase, that means it's phosphorylating. And so hexo prefix means 6, kinase is putting a phosphate on something. So we have hexokinase, which is correctly and logically named. So hexokinase is our first regulator. It's big, it's spontaneous, it's got a negative delta G, and boy oh boy, you can't reverse that. Now, something important to realize about regulators is regulators always have inhibitors, just like a boss. Otherwise, if they go unchecked, bad things happen. So, hexokinase is inhibited by its own product, and its own product is fructose 6-phosphate. So, this is a negative feedback loop that inhibits hexokinase. So, with that in mind, we'll go on to the next important regulation step, which is right here. And the name of this regulator is PFK, but PFK stands for phosphofructokinase, and this is a double phosphorylated 6-carbon molecule, or fructose, and its regulator is PFK. So something important to know about PFK is it too not only is a regulator, it is big, spontaneous, a negative delta G, and you cannot reverse it. It's also inhibited by ATP. Why does this make sense? Well, if you have an abundant amount of ATP, why would you want to move something forward when you already have what is needed prevalent? So, in this way, we have a really great system where ATP, if it's in excess, is an inhibitor for this enzyme. Last and definitely not least, we have pyruvate kinase. So, pyruvate kinase really isn't mentioned in terms of regulation, but the reason why these are highlighted so brightly is to allude you to the fact that these have a huge negative delta G, which means it's spontaneous and you cannot reverse it. It is irreversible. And so our pyruvate is our final irreversible negative delta G step. So it's important really quick to mention that when we have to go through the process of gluconeogenesis, or making more sugar, even if we have to go all the way back up this way, here, here, and here, these steps cannot be reversed. And MCAT often likes to pose questions to try and unfortunately trick you to see if you remember that these regulation steps do what they say they do. And you will for sure remember that these are regulators and you cannot reverse them. Thank you so much for watching my mini lecture on glycolysis, and stay tuned for the next one. Thanks.